So we have, and are very lucky to have, Dr. Micaela Martinez, who is also the new chair of our MIDAS steering committee, which is excellent. She is an infectious disease ecologist at Emory University. Her primary focus is understanding the drivers that shape seasonality in infectious disease systems, with particular interest in the impact of biological rhythms on disease. Her current projects aim to inform vaccination policy by revealing how demographic, physiological, and environmental factors intersect in epidemic-prone disease systems, including poliomyelitis, measles, and chickenpox. Dr. Martinez also conducts research on maternal immunity in infants and is building a statistical inference pipeline for studying vaccine modes of action. She utilizes cutting-edge statistical inference techniques and mathematical models to couple disease incidence data with clinical data to gain insight into the transmission dynamics of disease. We're very excited to have her. So if you want to go ahead and get started.
Sounds good. Thanks for that nice introduction. And feel free to turn on your cameras. It's always helpful for me when giving lectures to be able to see the faces of everyone that I'm speaking to. So let me get my slides up. So let's see. It seems like all of you have a great lineup this weekend. And I'm happy to give the second lecture. Okay, so we'll be building off the lecture that you had earlier today, the introduction to SIR models. And I'm going to talk a little bit about immunity and specifically herd immunity. And most of what I'm going to talk to you about today is likely going to be familiar to you because of the pandemic and everything you've heard on the news about herd immunity and vaccines. But I still would like to give you a formal lecture in that area in case there are some things that you didn't learn through the media. Okay, great. So let's first talk about transmission chains as a general concept. So a transmission chain as a concept is a set of host-to-host pathogen transmission events. And if we think about that through animation, you can imagine that you have one individual that is infected here, I'm illustrating this with the virus, and the one infected individual can infect others. Those infected individuals can subsequently infect more individuals, and it's that chain of events that we consider a transmission chain. Now, if we look at this, this first individual that was infected, we'll call them the primary infected individual. We can make an assumption here, just for the sake of this illustration, that if a person's infected, their infectious period is 1 week. So they're going to be infected for 1 week, and during that 1 week, an infected individual will infect 2 others. So what we have is this person all the way to the left, that primary infected individual, they infect 2 others in that first week that they're infected. So these are the secondary infections. Then another week passes, week 2, and the second set, the secondary infections then go on to each infect 2 others. So we go from 1 infected to 2 to 4, and this continues. That by at the end of 3 weeks, then we've had 16 infected individuals. I'm sorry, 8 infected individuals. So we're doubling. And from 8, we would go to 16. And so that's the case if you had each infected individual infects 2 others. And this brings up the concept of the basic reproductive number. And I'm not sure if you went over R naught in the last lecture, but I'll go over it again if you didn't. So the formal definition of the basic reproductive number, which we call R naught, which can be kind of confusing for American students, is like, why do we call this R naught? But that's because the British came up with this term and they call 0 naught. So that's why we call this R naught. So the basic reproductive number is the average number of infections caused by a typical infected individual. But most importantly, this happens in a population where everybody is susceptible. And so if, so R naught, you have to imagine this is everyone's susceptible, you have a new infection, and if you drop one infected individual into that fully susceptible population, how many others are they going to infect? So this is the type of scenario with an emerging infection, such as we saw when SARS-CoV-2 arose, that everyone was susceptible because our immune systems had never seen that infection before. That's very different from, let's say, an infectious disease like measles or the flu. It's not the whole population is susceptible. So the concept of R naught is really having to do with fully susceptible populations. And the important thing is, if R naught is greater than 1, that means that the infectious disease is capable and will spread through the population. And we're going to get into some of the math behind that in a little bit. So as I said, if R naught is bigger than 1, then that means the infectious disease can spread through a population. And over many, many decades, the R naught has been calculated for lots of infectious diseases. And this table here is giving some examples. But the one thing to know is that for each infectious disease, R naught can vary depending on the population, depending on the time period, and R naught absolutely varies from infectious disease to infectious disease. So for instance here, the first 2 lines of this table are showing estimates for R naught for measles. Measles is a highly infectious disease, and the R naught for that estimated in England and Wales in the mid-1900s was 16 to 18, meaning that one infected individual would infect 16 to 18 others. Whereas measles in Kansas, the R naught was estimated to be 5 or 6, so much lower. And this could have to do with the structure of the population in terms of contact rates and population density and such. Pertussis, which is also known as whooping cough, also highly infectious with the R naught of 16 to 18. Chickenpox, 7 to 8. All the way down at the bottom here, polio, which is what I did my PhD on, has a R naught of 5 to 6. Okay, so now just going back to this hypothetical situation where if we imagine each infected individual infecting 2 others, then we have this very rapid doubling. And that image that I had shown you where we went from week 0, 1 infected, to week 1, 2 infected, to after week 2, we went to 4, and then we went to 8. If we were to plot that with the x-axis here being the week and then the y-axis being the number of infected individuals, we see this growth curve, which we call exponential growth in this case, because we have an exponential doubling. And this is exponential because you can actually express this as an exponential function. So the number of infected individuals at time t, that's why I use a subset lowercase t, is equal to 2 raised to the t. So if we say 2 to the 0, so if t is week 0, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. And that would give us, that would recapitulate this graph that we have here. Well, what if this doubling just continued indefinitely? If each infected person just absolutely infected 2 others just unchecked, and that continued on and on and on and on, then this is what that growth curve would look like. And actually, by week 30, we would have infected over 8 billion people, which is greater than the world population. And I show you this because we don't see this type of situation happening really for any infectious disease. There are diseases like SARS-CoV-2 that will sweep as a pandemic, they'll sweep the world, but we're not seeing every person becoming infected with this kind of rapid level of growth. And what that tells us is that we don't have that consistent rapid level of growth. And one of the reasons for that is because, as I mentioned before, the definition of R naught is for a fully susceptible population. And as an infectious disease moves through a population, you have immunity that becomes gained. And we'll talk about that a little bit more. So this situation does not happen where whatever the R naught is, it doesn't stay that high indefinitely. So what does happen? So to think about how epidemics how epidemics truly play out in the real world, let's look at a very, what I would call a classic looking time series for an epidemic disease. So this time series is influenza in Jerusalem from 2001 to 2008. This is from a flu paper that was published in 2014. And I show you this time series because if you were to go and pull time series for measles, for polio, for chickenpox, rubella, so many infectious diseases, you would see them look like this. And so what happens? So what typically happens with epidemic diseases is we have recurrent epidemics. And so what do I mean by that? Well, first, what happens is if you look, so each of these peaks is an epidemic. So it's happening over and over and over again. And if we break down the shape of these epidemics, what happens is, if you follow my cursor, they always start with this epidemic growth phase here, this upswing. And we see that every time there's an epidemic, we have that exponential growth phase. And that exponential growth phase does not continue indefinitely. What happens is it reaches some peak at the top. And at this point is when we have a curtailment. So the epidemic ceases to grow and then it turns around and then we have this decay. And this decay then leads to a period of very low cases and low transmission. And we call this, oh, sorry, my mouse is, I'm losing my mouse. Here we go. So we call this section here the interepidemic period. It's that time between epidemics. So if we break down epidemics, we can always break them down into this 1, 2, 3 exponential growth, and then the peak when we have curtailment, and then the decline and the interepidemic period. And this typically happens like clockwork for infectious diseases. This is one of the things that my lab studies, which is the seasonality of epidemics. This is a flu time series that I'm showing you here. Flu, this usually is occurring in the winter when we have those peaks. There are other diseases like measles, which is in the spring, or polio, which is in the summer. But no matter what time of year epidemics are happening, they tend to have this very classic characteristic shape. And so earlier you were introduced to the SIR models, and we can model these types of recurrent epidemics using an SIR model. I have one pictured here with a susceptible, infected, and recovered class. And so one thing to note, so you already learned about the susceptible, infected, and recovered classes, but I wanted to talk just a tiny bit more about the recovered class, because the recovered class is the class that contains individuals that have immunological memory. That means that their immune system has seen the pathogen before and has some memory specific to that pathogen. And so our immune system keeps essentially a library of cells, of memory cells and antibodies that are specific to each pathogen that we've been exposed to throughout our life. And that exposure to these pathogens can be through natural infection or through vaccination. And we'll talk a little bit more about vaccination in a moment. And so just to give you a tiny bit of a hint of the biology that's going on in our bodies, I just wanted to mention B cells and antibodies. So B cells are the cells that produce antibodies. I'm sorry, B cells pictured here are the cells that produce antibodies that are specific to pathogens that we've encountered. And in the most simple sense, antibodies can glom onto viruses or bacteria and essentially prevent them from being able to successfully continue to infect cells within our body. And this is one of the ways that we can, our immune systems can fight off infections. But we also have lots of other cells in our body with other functions that go after pathogens as well. But the point being, once if you have an infection for the first time, you're going to have B cells specific to that infection and as part of your memory system. Okay. And so, as I mentioned before, that immunological memory, we enter into SIR models using this recovered class by accounting for individuals having immunological memory. So now let's talk a little bit more about the math behind the SIR models. I know that you got some of this earlier, but I wanted to break down the differential equations for you. So when you see a set of differential equations like this, it might seem a little bit overwhelming, but one of the things that I've found throughout my career, even as an undergrad when I first started working with SIR models, was that the best thing to do is to sit down with the SIR model and just break them down into the biological components, and that makes it much more digestible. So here, what I have are 4 different equations. The top one is the equation for the population size. So the total population size I'm calling N, and N is the sum of all of the susceptibles in the population, the infected individuals in the population, and the recovered individuals in the population, those that have that immunological memory. So that means that for any population we're looking at, we're binning everybody into one of those categories, S, I, or R. Now, equation 2 is showing the change in the susceptible class over time. I'm going to go through these more in the next slides. Equation 3 is showing the change in the infected class, and then equation 4 is showing the change in the recovered class. And I'll make sure that these slides are available to all of you if you want to go over these at a later point. But when we look at each of these equations, the best thing to do is say, okay, let me take one of these differential equations and break it up. What is it actually saying? So the change in the susceptible class over time, there are only so many ways the number of susceptibles can change. And this first term, which is mu times n, is representing new births into the population. So how can we get new susceptibles? Well, you can have babies born into the population that have never been infected with this disease. You could also have, which I didn't include in this equation, people who used to be immune, but then become susceptible because they lose their immunity, but I'm not including that. So here, all I'm showing is new births. So we're assuming that the only way we can get new susceptibles are by those new babies born susceptible. Now, the way that we can have individuals leave the susceptible class, so notice this middle term here has a subtraction sign, meaning that these individuals are being moved out of the susceptible class. And these individuals are moved out based on new infections. So these are susceptible individuals, S, that come in contact with infected individuals, and based on the transmission rate at that time, some fraction of those susceptibles will become infected. And then this very last term over here is the natural death rate. So individuals don't live forever, so we also have to account for the fact that people will die of natural causes. So we can have some of those susceptibles die of natural causes. Now, if we look at the infected class, we can similarly break this up into its components. We could have new infected individuals, and these are simply those individuals that are leaving the S class and they're moving into the I class. So we had the minus beta IS in that last equation. Now we're adding beta IS into the infected class. And we can also have infected individuals recover. So you can imagine if you have an infectious disease that infection only lasts a week, then you're going to have this recovery rate that is accounting for the fact that their body's going to clear the infection. We can also have infected individuals leave the I class because they die of the disease. And then we can have infected individuals leave the I class because they've died of natural death. And lastly, for the recovered class, we have individuals become recovered as their body clears the infection. So this is this gamma I term. And this term was subtracted from the last equation, but now it's being added into the R class because it's just the movement of individuals from one class to another. And then we have over here at the far right, delta R, which is natural death of those recovered individuals. Are there any questions so far? No, none yet. Okay. Well, I would encourage you anytime you're presented with a model, and especially if you in classes or for research are reading modeling papers, going and just writing out the equation and essentially taking every term and trying to figure out what the biology is that that term is representing can be extremely helpful. Okay, so now just to think about the I class a little bit more carefully, because the I class really is what we care most about, right? We're always tracking cases for infectious diseases. So the I class is really where the action is. So I showed you before the equation for the I class. We have, now I've moved things around. Oh, actually, no, I have it the same way as the previous slide. Oh, sorry. So the change in infected individuals over time. So we have that first term, which is a new infections. We have that second term, which is recovery. We have the third term, which was disease-induced mortality, and the fourth term, which was natural mortality. Now, what I'm going to do down here in the second part is to simply split this up into the parts of the equation that are things coming into the I class and the parts of the equation that are going out. So we have this beta SI term was the only positive term in this equation. So, and that was representing the rate in. But then this gamma I, alpha I, and delta I, these were all being subtracted. So we could put those all together, and that was a rate out. So by doing a little bit of algebra, and I've actually factored out the i's here, right? So by doing a little bit of algebra, I can isolate the rate in to the infected class and the rate out. And if we imagine this, and I know that there was some discussion in your last lecture about like water flowing in and out of a bucket. Now imagine this I class is some big kind of bubble, or I usually think about it as like your checking account. So your I class is your checking account. You have some rate of money into your checking account. You have some rate of money out of your checking account. And the size of that checking account is what we care about, like how much money are we going to have over time. And so we can, by looking at the rate in versus the rate out, we can know how is that I class either growing or shrinking, the same way we would know about our bank account. If you have more coming in to your bank account than you're spending, you know you're going to have money build up over time, right? But if you're spending more than you have coming in, you know your bank account is going to shrink. And it's the exact same way that we can think about that I class and the number of infecteds in the population. So now what I've done is I've given three equations with the left side is the rate in, and then the right side is that rate out of the I class. So if rate in equals rate out, then that means the number of infecteds is going to stay constant over time, right? Same way as the bank account example. If the rate in is greater than the rate out, then that I class is going to grow. And then if the rate in is less than the rate out, then that I class is going to shrink. Now, instead of expressing this, I'm going back instead of forward. So here now we have all three of these equations, right? And we know that depending on which side of the equation is bigger or smaller, then we're going to get a different result in terms of the I class. But instead of working with all three of these equations, we can simplify our lives by just saying, let's just take a ratio of the rate in versus the rate out. And if we just care about that ratio. So now what I've done is I've turned it into a ratio where the rate into the I class is in the numerator, and then the rate out is the denominator. And this is what we call the reproductive ratio. This is a rate, and we call it reproductive because we use the word reproductive to think about growth. So think of this as like the growth ratio for that I class. And so if the rate in is greater than the rate out, meaning that this ratio would be greater than 1, then that means that the I class is growing, and that means that the disease is spreading because you have more and more infectious or infected individuals. Does that make sense so far? Yeah, okay. And if there are any questions, feel free to unmute and ask. Okay, so now this brings us back to R naught. And actually now we can really conceptualize like why this R naught greater than 1 is meaningful. Because when with R naught, we're in the calculation of R naught, it simply is this reproductive ratio, but under a scenario when everybody is susceptible. So remember earlier, I told you that we use N to represent the population, the full population. So if we say N is 1, and then S, I, and R are just fractions of the population, well, if everybody is susceptible and N is equal to 1, then that would mean that S equals 1 for a scenario of R naught. And so R naught is simply this equation, this ratio, but where S is equal to 1. And so R naught can be written out as beta over gamma plus alpha plus delta. And that is for the set of differential equations that I gave you, but we could make any more extensive set of differential equations for an infectious disease. But no matter what, all you would do to calculate R naught is to figure out that those terms in your equations that are the rate in versus a rate out, and then you turn those into a ratio. And then that's always what is used to calculate R naught, regardless of the infection. And so does that make sense so far? Yep. Okay, cool. So now this takes us to thinking about vaccination and herd immunity and how we could actually do the math on vaccination. So we have going back to this reproductive ratio, is the I class growing or is it shrinking? We know, given this this quite simple equation, that in order to make the I class shrink and to get an infectious disease to start going away, what we need to do is we need to, make this ratio smaller than 1. And to do that, what we can do is we can target this numerator, essentially trying to make this numerator in the fraction smaller and smaller and smaller and smaller. And so one way that we can do this is we can target that size of that S value, the size of that susceptible class, and shrink that because its largest would be 1 in the case of R naught. But if we shrink that smaller and smaller and smaller, then hopefully we can get to a point where this overall ratio becomes less than 1. And so this is the goal of vaccination, or one of the major goals of vaccination, is for vaccines that actually reduce transmission, then they can shrink that susceptible pool. And here on the left are a list of our vaccine preventable diseases. We have in the United States, routine vaccination for chickenpox, for TB, rotavirus, polio. Many of these things are in our infant vaccination schedule. And most of you have likely been vaccinated against many of these things by the age of 5, but mostly in infancy. Okay, so our whole goal is to make this ratio smaller than 1. And like I said, we're going to do that by hitting this S and making it smaller. And so this brings me to the concept of herd immunity, and I just want to check the time. Okay. This brings me to the concept of herd immunity, which is something you've probably heard a lot about in the news, especially when we were first coming out with the COVID vaccines. All the talk on, NPR and CNN is, well, are we going to reach herd immunity? Are we going to reach herd immunity? And we'll get to that towards the end of this lecture. But the idea behind herd immunity is that a sufficient portion of the population is immune, and a sufficient portion of the population is immune so that S is small enough that the I class isn't growing, the disease isn't spreading. But we can get herd immunity through vaccination. The whole point is we need to immunize people. That could be through natural infection, it could be through vaccination, it could be, or a combination of those things. But herd immunity occurs when the S class is sufficiently small that the disease can no longer spread. It makes transmission unlikely. And the important thing is going back to this equation, to get to that point where we'll reach herd immunity, S just needs to be small enough that this fraction is less than 1. That doesn't mean that S necessarily needs to be 0. It doesn't mean everybody needs to be vaccinated. So this is really important because what herd immunity does or tells us is that we don't necessarily have to reach every person to stop transmission. And just to conceptualize her, and I'll go over that a little bit more, but just to conceptualize, oh, my slides keep acting up. Oh, here we go. I accidentally advanced them too far. Conceptualize herd immunity. Here is a image that I pulled from UC Davis's website explaining herd immunity. And so here at the top, when nobody has immunity, so you drop an infected individual, which individual is shown in fuchsia, into a fully susceptible population. So everyone in blue is susceptible. Then that infection can just spread like wildfire. Everyone is susceptible, so the infection goes unchecked. But if we have some immunity in the population, so imagine now these green individuals can't be infected. So they essentially act like blockers for sufficient transmission in the population, because now this infected individual, he or she, when they interact with an immune person, they're not going to transmit, and then that keeps that transmission train from continuing, so there's less efficient spread. But if we have a sufficient number of immune individuals in the population, then we can stop transmission to such an extent that we will not see disease spread whatsoever. And we can actually get to disease eradication, which is when we actually drive an infectious disease to extinction. And so in order to have disease eradication, once again, we need to have this fraction be less than 1. And we can have essentially 2 types of disease eradication. You can have global eradication, where you've gotten rid of that infection all across the globe simultaneously. So you've made that reproductive ratio less than 1 everywhere. This is what we are able to do with smallpox in humans, in rinderpest in wildlife. But we could also have local eradication, where the susceptible pool is small enough in either local municipalities or individual countries that you locally stop transmission. This is the case for polio. Much of the world has been polio free over the last, it varies. Some places have been polio free since the 70s, some have only been the last decade, but we do still have polio in some parts of the world, but there's very isolated populations, or in, I shouldn't say isolated populations, but in localized countries and populations. So we can have local eradication where you get rid of it in a particular population or place, or you can have global eradication where you get rid of it everywhere. But the most important thing is that in order to have disease eradication and in order to have this reproductive ratio less than 1, we need to know, well, what fraction of individuals do we need to vaccinate to make this thing less than 1? And what we call this, the fraction of individuals we need to vaccinate, is the critical vaccination fraction, or the critical vaccination threshold. It's that critical point where once you vaccinate X number of individuals, then you're gonna have that disease start to fall away. So in order to do this, okay, so we take our equation for the reproductive ratio, and what we want to know is how small do we need to get S to have this ratio be less than 1. So what I'm going to do is I'm going to isolate S to one side of the inequality. So I moved everything else to the other side. And so now and also the sign of the inequality has flipped, because this is just inequality math rules. So now we have, in order for the reproductive ratio to be less than 1, that means that S, the fraction of susceptibles in the population, needs to be less than gamma plus alpha plus delta divided by beta. So this is those top ones, just to remind you, the recovery rate plus the disease-induced mortality rate plus the natural mortality rate divided by the transmission rate. And for infectious diseases, for each infectious disease, these values are going to be different, these parameter values. But for some of these parameters, we can get those values from like clinical information. For other parameters, we get them through modeling. So for instance, if you have an infectious disease that has 1 week long infectious period, then that means that recovery rate is 1 divided by 1 week. So we could actually go out into the world and observe people that are sick and say, okay, well, how long do they have this infection? And get estimates for some of these things so we could actually do this math. Okay, so S needs to be less than this fraction over here. And so what that means is that there's a critical transition point where S is equal to that fraction. So this threshold, that's like this sweet spot, is when S is equal to that fraction. And if we look at the structure of this fraction, if I were to go back several slides, what you would notice is that this fraction is incredibly familiar because it's just the reciprocal, just the flipped version of our equation for R naught. So we could actually simplify this and say the critical number of susceptibles or fraction of susceptibles is just equal to 1 over R naught for an infection. And so S critical is the fraction of the population that's susceptible. So we know how small we need to get that. And if we're going out and we're vaccinating individuals, so we're moving individuals from S to a V class by vaccinating them. If you are, let me put it to you this way. Imagine everyone in a population is susceptible. And the only tool you have is to be able to vaccinate them to make that S class smaller. And so if all of your population is either going to be in a susceptible or vaccinated, and the susceptible fraction is 1 over R naught, it's that fraction, then that means the critical vaccination group, or the fraction of the population you need to vaccinate, is 1 minus 1 over R naught. Because 1 over R naught is the fraction susceptible, and 1 is that population size. The total, if you take all the fractions of the population, they're going to add up to 1. So this here, this equation V critical, is the equation for the fraction of the population that we need to vaccinate in order to eradicate or eliminate an infectious disease, to get that infectious disease to keep from being able to spread. And that is that same fraction that we need to calculate to get herd immunity. I think I have something in the chat. Are there any questions? I only have like a couple more slides. Okay, because I do want to get to this exercise I have at the end. So I gave you that equation for the V critical, so the fraction of the population we need to vaccinate for herd immunity. And now going back to that table I showed you earlier with the R naughts for different diseases and different locations, we could simply use these values and plug them into that equation to get V critical. So for measles, we would need to, with measles with the R naught of 16 to 18, we would need to vaccinate about 94% of the population to have herd immunity. If measles in Kansas, which had a lower R naught, we would get away with vaccinating only 83%. For whooping cough in Maryland, we would have had to vaccinate 94%. And so notice that the bigger the R naught, so the more infectious a disease is, the more you have to vaccinate to get rid of it. And so actually, I just want to click to the end. Okay. So the thing that's most important, though, is like for a practical standpoint, is, well, you have a vaccine, but what's the actual efficacy? Because it's not just about going and just because a person is vaccinated doesn't mean that they're immune and that they're not susceptible to the infection. So this is where vaccine efficacy comes into play. And so vaccine efficacy accounts for, it can account for multiple things. For vaccines that fail to provide sufficient immunity to protect the individual from infection, vaccine efficacy can also account for different modes of action for vaccines. There are some vaccines that are very good at protecting from disease, like actual symptoms, but might not be so good at actually protecting from infection. So when we think about vaccines in these equations and vaccines being able to cause herd immunity, that's really, those are really vaccines that are protective from infection. And we will also hear those referred to as transmission blocking vaccines. Okay, so if we had perfect vaccines, then this V critical, meaning that every person that's vaccinated, they're going to be fully immune and not be able to get infected. If vaccines were perfect, then this V critical would be 1 minus 1 over R naught. But in fact, we have differences in vaccine efficacy. So when we think about this V critical, so the vaccinated individuals have true immunity, pure immunity, and they're not susceptible to infection. In fact, that actually needs to be broken down into the fraction of the population who's been given a vaccine multiplied by how efficacious that vaccine was, the effectiveness. So imagine if you have 90% of the population is vaccinated, but only half of those individuals actually have vaccine that gives them protective immunity from infection. Then really this V critical is only going to be that 0.9 times 0.5. And so this is how we account for differences in vaccine efficacy. But what we really care about in public health is how many people do we need to vaccinate. So then what we have to do is we have to take this fraction of the population administered vaccine and isolate that into one side of the equation by itself. So that's what I've done over here. So vaccine administered is going to be 1 over vaccine efficacy. And then we have that V critical, and I put the actual, instead of just putting V critical, I put the 1 minus 1 over R naught. So when we want to know how much vaccine, what fraction of the population to give the vaccine to achieve herd immunity, this equation down here is what's going to do it. You have to know the R naught, which is going to tell us about how infectious that disease is. And we have to have that efficacy number. And this efficacy number is relating to how, what fraction of those vaccinated actually have immunity that's going to protect from infection. Okay, so I think we only have 1 minute left, but I would like you to do a little exercise, and you can do this now or later, but I just looked up this morning. Okay, so what are the R naughts for each of the SARS-CoV-2 variants? And this was a recent paper from the Lancet. So if we look at the original strain of SARS-CoV-2, we had an R naught of 2.5. And then if we look at the Delta variant, we had an R naught of 7. Then if we look at Omicron, we have an R naught of 10. And we also have a lot of uncertainty around the vaccine efficacy for our different vaccines against each variant, right? So what I would like you to do is to take for each variant, so you have 3 different R naughts, and then calculate with a fraction of the population where that we would need to administer vaccine. So vaccine administered based on 4 different efficacy numbers. If we had 100% efficacy, 90%, 70%, or 50%. And the thing to note is when you're doing this calculation, when you put those numbers in as efficacy, you need to put them in as a decimal. So 100% efficacy would be 1, 90% would be 0.9, 70% would be 0.7, 50% would be 0.5. And so you can do those calculations. I'm sure it would take you a few minutes. But just because of the sake of time, but I do want all of you to go through and do these calculations. But I put the answers on the next slide because I want to actually talk about these as we wrap up. So, okay, if we do plug those in, right? So we have the 3 different R naughts. For the OG SARS-CoV-2, we had 2.5. For Delta, we had 7. For Omicron, we have 10. And then I just plugged into that equation the different efficacies. Okay, so the first value is, so if we had a R0 of 2.5 and 100% efficacious vaccine, to achieve herd immunity, we would need to vaccinate only 60% of the population. Once our vaccine efficacy drops down to 90% efficacious, then we would have to vaccinate 67%. Once we drop down to 70% efficacy, it goes down to 86%. But look, once we reach a 50% efficacy, we would have needed to vaccinate 120% of the population to achieve herd immunity, which tells us that that's impossible, right? We only have 100% of people. So, which tells us that for R0 of 2.5, once our vaccine efficacy gets as low as 0.5 at 50%, we cannot achieve herd immunity with that vaccine. Now, if we plugged in for the Delta variant, an R0 of 7, what we see is that here we reach this 122% once we get a vaccine that's only 70% efficacious, right? So what this is showing us is that as we up that transmission rate, as we up that R0, we have to vaccinate more and more. And then when you put that, or you take that with the fact that our vaccines are not fully effective, then that can put us in scenarios where herd immunity cannot be achieved. And so then with Omicron, if we had this is a perfect vaccine, we would still have to vaccinate 90% of the population to achieve herd immunity. And once we drop to a vaccine efficacy of 0.9, we would have to vaccinate every single person to achieve herd immunity. So this is why when we talk about infectious diseases, like SARS-CoV-2 and the variants, it becomes very, very important to be realistic when we're considering the possibility of herd immunity and the way that our vaccines work. And I think we're 3 minutes over, so I'll leave that. I'll answer any questions if anyone has any, and I'll leave you with that.